Hi, everybody. I'm happy you could all find the room. I'm going to go through some, it's not really a tutorial, it's more of a brain dump on what we do for the drone data collection and the IoT sensors and tools associated with all the gadgets that we've been burying in the ground and putting on poles. A lot of this is work that Tom DeFonte and Larry Smarr allowed me to play with through the 10 years at the National Research Platform and the Pacific Research Platform before that, back when we had funding. And so it turned out it was good exercise for precision agriculture. And so I've been a drone pilot for probably 15 years. Not a Part 107, but just a recreational drone flyer. But I've used it at my own home construction in New Mexico, where I would create 3D models of the build lot that I worked on, and made sure when I put chalk lines down on the ground that my SketchUp model fit into said things. And I've found so many errors using the drone to check my work. Yeah, I drew a line 1 foot on the wrong side of a pin a couple of times. And so it's been a very helpful tool for the drones. And then the IoT sensor network stuff. I live in New Mexico. Water is like gold. And if you have it, you don't want it leaking out or spilling or evaporating. So I use it to water tank levels and well depth to water. So I've created a sensor network at my site to make sure that I have it when I need it. So the drone that we're using on the Iron Horse Vineyard is pretty affordable. It's like $6,132 before tariffs. And now bans. But luckily this was not funded by any federal agency. This was funded by Scenic. So we were able to purchase the Mavic 3 multispectral. This drone has a 24 or 20 megapixel RGB camera, and then 4 5 megapixel sensors for the multispectral bands. And so it does green, red edge, and near infrared on those spectral bands. And with that combined with the RTK module that's on the top, we get 1 centimeter accuracy in the flight paths. We use an N-trip service. It's actually managed by UCSD. It's a national scale service that gives us the corrections that if your drone has Wi-Fi connection or you have your cell phone and you share a Wi-Fi link to your controller, then it can get those N-trip corrections in real time, and it positions your drone accurately XYZ anywhere you want. And then we use software to have a repeatable flight path that runs around the same path, exactly same altitude, exactly same location, so we can study things over time and know that the technique of collecting the data has been the same. So here you can see Joyce Sterling, the owner of the Iron Horse Vineyard. This was one of our first flights at the vineyard, and on the right-hand side, you can see the UGCS. It's a drone flight planning software that understands how to do terrain following, which is extremely important in a hilly environment like the Iron Horse Vineyard. It's got some good vertical changes, and when we first started flying, I was using SRTM, digital elevation model, which is, I think 90 meter. And the drone kept on stopping because its accuracy for terrain following was at the 90 meter resolution. And the vines kept getting too close to the drone, so it would just stop. And then we just went to GS and grabbed the 1 meter elevation model, and it's fine after that. Some other software we use is Pix40 Fields. That actually, for every flight you process the imagery in, it creates a digital surface model. Digital elevation model is using a terrain plus minus vegetation and buildings. So you're not seeing the tops of the trees or anything else. They subtract all that stuff from a digital elevation model. Digital surface model includes all that, and you really want that when you're doing flight planning, so you don't run into telephone poles and trees and things like that. The Mavic 3 series has really good collision avoidance cameras. So no matter how hard I try, I've not got it to run into a telephone pole or a tree yet. So it'll just stop and say, fly me away, which is really good. It's not something you want to crash into. The UGCS is the flight path mission planning software. And this is, we got a educational partnership deal. I think it was like $1,500 or something like that. And Christap, I forget his last name, really nice guy that created this software, has been consulting with us on how to fly in a vineyard to collect data capable of creating these 3D Gaussian splatting digital twin representations that we're trying to do. And basically we want to create a digital twin of the vineyard above ground and below ground that includes the sensor data, and do that over and over through time so we can see what's changing, use the photogrammetry from the drone to then detect changes in the vegetation and then redeploy the sensors at locations where we're seeing anomalies or have questions. So we want to, instead of burying sensors all throughout the vineyard, which can get expensive and hard to upkeep, we want to use the drones to guide our sensors. This is a photogrammetry flight. It's really nice. We've got all the blocks of the vineyards all defined for us as KML shapefiles, and we can import those into UGCS, and then we just kind of, you can select that and create a perimeter, but we found it's more accurate because we have to adjust everything to avoid the trees. Some of these blocks go underneath tree limbs, and so we really don't want to just use that as the edge. We go in there and create, just click around the perimeter of the block that we already have in a GIS file, and then we can rotate the flight path, set the ground resolution, or set the spacing, and then you synchronize that with the drone through Wi-Fi, and then you can actually watch the drone flight in real time from your laptop where you generated the file. You can also launch the drone from the laptop, which, if you have all the right permissions, means if there's a person at the vineyard and I want to be the pilot, I can just use remote desktop into the laptop and I can push the button and it'll take off and fly. You have to have somebody physically with eyes on the drone to be able to do that. Remote piloting, there's ways to get licenses apparently, but I haven't gone that far. And it's actually nice to have, you have to have somebody there to swap batteries, because most of these drone flights take longer than 45 minutes, which is the flight time. This is another technique called circlegrammetry. This is the one, you can define the overlap of the circles, the radius of the circle, and the number of photographs it takes in the circle. And this is supposed to allow you to create better overlapping data sets for doing 3D reconstruction. The software for doing this still gets confused because circle grammetry is a fairly new technique, but the UGCS folks are highly aware of this, and so we're working with them to figure out what are the flight parameters, how high above the vines do we need to fly, you just can't fly. Normally when you're doing vegetation indexes, you're flying a grid pointing straight down or maybe at a slight angle. But grapes don't grow on the top of the vine. And so we want to fly as close as possible to get the sides of the vine to be able to record all the information that we're looking for. And so circle grammetry is the technique we're trying to perfect. We finally did get a Gaussian splatting rendering of a section of the vineyard, and there's a box that you have to uncheck is sequential imaging. And basically it does more brute force calibration of all the photographs against every other photograph, so it takes longer to do the calculation and create the point cloud that you're going to use for the camera positions. But you know, it's just one box you uncheck and it seems to work better. I'm sure there'll be more. The three-dimensional Gaussian splatting is one of the latest, coolest technologies for doing 3D reconstruction, not creating OBJ files, the actual texture map models, but it's a real-time rendering technique that allows you to see individual pine needles on a pine tree, which you couldn't do in an OBJ or any other digital twin before. So we're really excited to be able to continue developing the techniques to collect data and then process it into this format. This is a low altitude terrain following. This is where I put in the 1 meter digital elevation model from USGS, and we were able to get 1 meter off of the top of the vines. And at the top of the vines is also where there's a bunch of steel wires and poles running. And so you want to stay clear from them. The problem we found when we flew that close is the prop wash was blowing the vines all around, and so the data was useless. So we have to be able to figure out ways of flying offset from it and maybe use a telephoto lens on the RGB camera to get in closer. But that's not going to work because the multispectral cameras aren't telephoto. And so maybe contact lenses or some other technique. So we're learning a whole bunch about how to collect the data. Now, Pix4D Fields I mentioned earlier, this is a processing software that we just upload the RGB image and the 4 individual multispectral bands into it. It automatically generates NDVI vegetation index. This is basically it's used for highlighting stress in the vines. You can see where there's a lot of growth in the canopy. You can identify places potentially that are getting too much water, which is a big problem in vineyards. If you get too much canopy growth, they're going to be shading the grapes. You have to go out there and prune more than you would if the amount of water was consistent across the entire block. So the Pix4D Fields will automatically generate, I think it's 9 vegetation indexes and a digital surface model. But you can also put in your own formula for the band math that you do, so you can custom tune an algorithm that is figuring out exactly one specific band combination that you're looking for. Maybe I think one of the things that I'd be interested in is Emery has a hyperspectral camera with his vineyard or farm, and we could create a proxy to map the hyperspectral data of a flight to the multispectral camera. And then we could create that algorithm to do the identification that represents a hyperspectral tuning that we know is detecting what we're looking for, and map that down to a much cheaper camera. How much is that hyperspectral camera? More dollars than we have. So yeah, the vegetation indexes are very interesting. And I'll get to some slides that show. This is a PDF report that is automatically generated from the Pix4D fields that gives you the overview of these different vegetation indexes. And so green normalized vegetation index, leaf chlorophyll index. Some of these, you start seeing these little, there's structure in these, and then that's just the orthomosaic over there. There's the digital surface model. But this one here, you can see these kind of halos that we thought at first they have this sprinkler system for frost protection. And we thought, oh, those might be at the locations of where all the sprinklers are, and that's kind of creating a halo. Nope. They're much smaller footprints than the sprinklers. I purchased a 1 centimeter RTK surveyor pole, which I'll show in the, and basically we just went down a few rows and geolocated all of the sprinkler locations so we could then overlay it into this map, and they did not align. So that's still a mystery. We have some soil microbiome folks that are going to be visiting soon and doing some soil sampling, and maybe they can identify what is different on the inside versus the ring surrounding those halos. Maybe it's old stumps from trees from 100 years ago that are still being represented in the soil. And this was at a time where there wasn't a cover crop on, so this is bare dirt, and we're seeing this in the dirt, not in the vegetation, the vines itself. And that one on the end, that's the digital surface model that we can plug in the UGCS software to avoid the terrain at much higher resolution. Basically, probably 3 centimeter vertical resolution right down to each grapevine, as long as it's not blowing around. And so, yeah, the Pix4D fields, we have 25 seats licensed, and so Emory and a couple other folks are using this for their work. We can just add an email address, and then they can download the Pix4D fields software to their local laptop and run it. And then UGCS, they're very flexible. They'll give us another copy if we need it, but right now we're just using remote desktop to log into the Iron Horse Vineyard system that has it set up, and we can generate any maps we want. So another tool we use is WebOdium. It's an open drone map for a web service. This is what I've been using for years. We've had this running on the National Research Platform as a service, and it allows you to upload your drone data, and it'll automatically generate the NDVI vegetation index. This is the salmon habitat from the Iron Horse Vineyard, and you can see, you can download orthophoto, a surface model, a point cloud, a textured model GILTF, the camera parameters, the camera shots, quality report, all assets. And so it gives you a 2D map, a 3D model, and a generated report. So this is an automatic service that you have to upload the data through a web browser interface. And so this is a orthophoto of the salmon habitat. So this is the vineyard and the surrounding area, but down below there is the Green Valley Creek that's been modified into a very nice playground for the salmon. And they put all kinds of structure in there and created trenches and canal ways, and took out hundreds of truckloads of dirt to make a low-lying fish habitat. This is the NDVI vegetation index from that same data. And then this is the point cloud. The point cloud is so dense you can barely tell. It's almost like a Gaussian splat. It does a better job than the 3D orthophoto, where it starts clumping together, and you're instead of splatting the data sets in a Gaussian distribution to get the really high resolutions, it's trying to create a surface out of the data and then apply the texture map to it. But yeah, so all this is a in-browser web interface that allows you to manipulate the results. And here you can actually see all the tracks that you see. That's of them building the salmon habitat before it was finished. Scale ODM is a Kubernetes native API version of this same thing. And so this is the Scale ODM Helm chart that makes it simple to deploy. It's also using, instead of you having to upload the data through the web browser interface, you drop your data in an S3 bucket on Nautilus on the NRP cluster, and then it'll pull the data using your bucket name and API key, and then it'll return the results to that same bucket. And so this allows you to kind of script it and not have to deal with the web interface to automate. When you're moving a lot of data and you want to do it on a regular basis, you really don't need that web interface. You just need an API that makes it easy. So this is the modified Helm chart that we've made that allows you to deploy it on the National Research Platform. We haven't hooked up the S3 buckets. This is just a week old. Mohammed and I are working on this, but pretty soon we'll have this as an example for anyone to deploy in their own namespace. So this will make it a lot easier for people to process. And WebODM, the Open Drone Map project, is open source. So we should be able to extend that. And actually 2 days ago, I saw somebody has made a feature request for a WebODM or Open Drone Map for Gaussian splatting. And so hopefully, if we get enough thumbs up on that feature request, we'll get Gaussian splatting support inside there. QGIS is a mapping application that's from the Open Source Geospatial Foundation. It's free GIS tools, as powerful as ArcGIS, very expensive commercial product. Includes a lot of back-end processing from a project called GRASS, which used to be Army Corps of Engineers tool. And this is what I've been using for decades, I guess, at this point, to create maps that can be published into Web Map Services and or just create OpenStreetMap or standard map layers. It does processing, labeling. You can combine raster images. There's a lot of background data, and you can put all your shape files in there and annotate. You can edit your own shape files. So this is the Iron Horse Vineyard. They provided a 2013 version of this map to us, and then they had a photocopy of a new version that they didn't have the actual digital asset for. And so I went around and I modified all the edges of this to cover the exact area where the vines were growing. And so here you have a layer here, then the Bing XYZ it's just a Bing background map that gives you a nice high resolution photograph. The GeoServer is an open source project. I like open source, I can afford it. This is a place where you can publish your data in a web map service. And what this will allow, we use another tool called Thingsboard that can pull these web map service maps into our IoT dashboard that has a map with all the locations. And so this is a pretty simple deployment for getting an extremely powerful web map service. GeoCat Bridge is another, I should mention, this is GeoServer 3. It's a brand new version of GeoServer, and it has some new features that allow us to use this GeoCat Bridge and the QGIS version 4. So these are all brand new. Actually, QGIS, I think, is still just a release candidate. And so these are the latest, greatest tools. And what this does is it's a plugin for QGIS, and it will, you select the layer you want to publish into the GeoServer, and you push one button, and it's pushed. And so this allows you to publish the processed data into a location that makes it easy to put into any other web service for correlating the NDVI imagery and the sensor data in the same visualization. So here I'm selecting the blocks, and this is the GeoCat Bridge for QGIS. And I can add my own metadata in here, so it's a metadata editor. You can create templates to pre-populate the metadata. So we're going to be doing this over and over, so we'll have the metadata will be pretty much static, except for the date. And then the next thing is the connection, and we just pointed at geoserver3.nrpnautilus.io/geoserver, and then put in the authentication username and password, and then save it and publish it. And it pops out here as Iron Horse. These are a bunch of, the GeoServer comes with some generic shape files built into it. But the features, it does web map services, 2 different versions, tile services like OpenStreetMap is a tile-based system, web feature servers, and web coverage servers. So this is raster, this is vector, this is tiles, and those are maps. So you have all these features. You can create maps from all the layers that are in there and push that out through WMS, or you can do, if we fly the entire vineyard, we can create orthomosaics and timestamp them so you can see a web map, web coverage server from each timestamp. And then we can flip those layer timestamps over and over and do comparisons. What was it like this year? What was it like the next year? So, or just the next week. Depends on how fast we can fly and collect the data. And so, yeah, for here, the map formats, I mean, just, it's a very long list of ways to spit that out. OpenLayers is one of the most popular open source map tools. It will run those out. It also has, for all these services, they have these get capabilities files. If you click on one of those version numbers, you'll get a get capabilities file that you can just paste into ArcGIS or QGIS, and it'll pull that whole data set in. And you'll be able to zoom around in it. It does tiling. It does multi-resolution geotiffs, embedded pyramid files, so it's extremely efficient. You're not waiting a long time for it to load a whole file. It'll just, if you're zoomed in real close, it'll just send you the chunk that you want to look at. And so this is the output of that, which is the layer, the blocks layer with the labels embedded as a JPEG PNG. So if I come back here, JPEG PNG is right there. So that's just one of the many formats that it can spit that out as. So now we're going to switch from drones to IoT. We use LoRaWAN. It's long range, low power, low bit rate sensor data. And the most popular tools for managing that is ChirpStack. And a lot of times you'll find ChirpStack embedded in the hardware LoRaWAN gateway, or you can run ChirpStack in a Docker container, which we do at the Iron Horse Vineyard. We have a enterprise gateway, a Kona enterprise gateway. It's really ruggedized environmental enclosure. It's got a ground lug for hooking up your lightning protection. It's got surge suppressors built into it. So it's a very nice, moderately expensive component that we chose to put up on the top of the building that you definitely don't want to get struck by lightning and burned down. The other system that you can use is a Raspberry Pi based ChirpStack OS. Basically, you flash the Raspberry Pi with this as its OS image, and everything's working out of the box. And so it makes it really inexpensive and simple. Then you just put it, you can buy curated kits that have a Raspberry Pi 4, and then all you have to do is hook up the whatever antenna you want to it. It comes with a power supply, and then you flash it with this OS, and it starts imaging. So this is the Iron Horse Vineyards. This is a Docker container running in the vineyard, and basically ChirpStack is capable of doing a multi-tenant. So if you have a bunch of sensors that different groups are taking advantage of or supplied to the test bed, you can have them all being aggregated, and then the different tenants log in with different credentials, and they'll be able to see just those. Typically, users on NRP, we're not giving users access to the ChirpStack Docker running. It's on a Mac Studio running in the Iron Horse Vineyard office. The nice thing is this Iron Horse Vineyard is connected at 10 gigabit a second. And so we did that so we can move all the drone data quickly out, and so we could use remote desktop to teleport into and operate the laptops and the Mac Studio for doing data processing and for remote control of the flight planning software. So this is the Iron Horse Vineyard tenant, and then you create an application for each one of the sensor models. And so we've got this top one is a EM300 LoRaWAN pulse counter, and this can be hooked up to a legacy pump. And basically it's a little Hall effect sensor. It can see an impeller spinning by, and you can calibrate that for every rotation. Is it a quart? Is it a gallon? How much flow is coming out of this pump by the pulses? The EM500 is a CO2 sensor. This does CO2 concentration, temperature, humidity, and barometric pressure. These we mount in the canopy above the ground sensors we bury. So we're trying to nest all the sensors in locations, so we're gathering as much information about the plants directly next to these sensors, either side of the sensors in the ground and right above them. So if we get too much vine growth, the vines will block the sun, and we'll get a humidity buildup in the canopy, and this sensor can pick that up as a bloom of humidity. And another one at the other end of the field where it's drier, it's not going to get as much vine growth, and you'll see less humidity in the canopy. And if there's too much vine growth, they have to send out people to lay hands on the vines and prune them back. So they actually prune back just leaves or entire canes to give it more breathing area and to get sunlight onto the grapes themselves. So you're going to get more sugar production if the grapes are getting sunlight. So the EM500 is a pipe pressure sensor. That's going to be kind of a combination with the pulse counter. We haven't hooked right now the pulse counter isn't hooked up to anything. They've been fixing some pretty major infrastructure. Their pumping station, it was built in, 1972 or something. And so we're trying to be able to predict if there's clogs or leaks based on historical data of when they're running the pumps. But it's pretty complicated. We might have to deploy a lot more pressure sensors to be able to get a good map of it, because they don't open all the valves. They open up a zone and they measure a zone. And so there's no sensors on the valving, so we can't really predict if there is a broken pipe or a missing spray head and it's just flying out the top of a pipe. And so that's going to take some more work to integrate a water management solution, but we have the sensors to start looking. This is a seismic sensor, WISE block. This one has been a little problematic. The instructions are in Chinese. The device refuses to join the network, and tech support has a language barrier. But we'll eventually crack that one too. It is a pretty inexpensive device, but it would be nice. What these are used for is to automatically shut down systems. If it does get a shake, it'll shut down pumps, shut down generators, things like that. It's not going to predict anything. It's going to sense if something happens and kind of pull the plug on anything that could get messed up. Okay, the SDI-12 LS is basically, this is a solar-powered SDI-12 converter module that in this case is talking to a Teros 22 soil water potential sensor. The group in Washington State University spin out, they basically, it's like a digital route. It tells you how absorbable the water that's in the soil is to the roots of the plant. And so combining this, we bury these in the ground right next to a soil moisture sensor that gives us the absolute moisture, conductivity, and temperature. And this also has temperature. And we kind of drill in 2 holes and get them within like 6 inches of each other at the same depth. And so they're giving us the absolute moisture value and the absorbability of that to the root itself. And so it's pretty cool. The Meter Corporation is the name of the company that makes these. They have all kinds of really cool precision agriculture sensors, including these little sensors that clip on a leaf of a tree or a grapevine, and they'll give you the moisture of that. And also, they have like CO2 transpiration, basically seeing how the roots are absorbing and exhaling the leaves in the stack, and so they've been working on precision agriculture sensors, but everything they do is designed to hook up to a data logger, and that's a lot more work to go around in the field and collect the data from a data logger. So Dragino has this SDI-12 LS, which is solar powered, It's an SDI12 to LoRaWAN converter box. And so what we do is we figured out how to program the SDI12 box to send commands to the probe to grab the data. And it's really ugly hex coding. You have to basically figure out from the manuals what code you need to send to make it send the data once every 10 minutes or whatever it is you want that data collected in. And then you got to parse it. And so there's all kinds of evil things you have to do. I should link a spreadsheet in this before I publish it. But there's some things that I've learned through brute force to make these SDI12 sensors work. The next one is the Dragino SE01, and that's also a battery-powered or solar-powered. We're buying the solar-powered ones. Instead of a 10-year lithium iron sulfur battery, they have a lithium battery, much smaller, but it's solar-powered, so it can run 6 days without any sunlight. And then the maintenance window on those is even better. If we want to send the data faster than the sulfur batteries can last for 10 years at, and so we've opted for doing the solar powered. But these things are soil moisture, conductivity, and temperature. And this particular one, the SE01, is a single probe. There's a SX01 that is a single solar-powered LoRaWAN converter, but it's got 4 probes on it. So you have one transceiver, and each one has an address. And as you're setting these up, you plug in the sensor that's on address 0, and you change it to an address 1 through some hex codes that you slam into it to change its address. And so we have, this one is actually set up. We have 4 individual applications. This one is SEOXLS. That one is the quad probe, and we decided you can group these anywhere you want. We were just experimenting with what made it easier to reflect this data. It turns out it really doesn't matter how you do it to get the data out. The SEOX is the same actual sensor that's hooked up the SE01, but there's just more of them. And so this is the application for the EM500 CO2 sensor. And here we're just looking at link metrics. You're getting the signal-to-noise ratio, RSSI, and the number of payloads it's received. And then you can see the frequency ranges and basically a bunch of RF statistics. So the sensor networks it's good for more than just the payloads that the precision agriculture is looking for. It will show you all kinds of RF information. So if you're trying to plan how to deploy a bunch of LoRaWAN sensors, you can use this for modeling an RF digital twin of your area. And so you could even imagine hooking up a LoRaWAN sensor and then flying it around with a drone to actually locate it where you want and get the signal to noise ratio and all the other RF information back, so you could do planning just by flying one sensor around and seeing where you have dead spots. So this is the same sensor. This is the devices. So we have all these are all CO2 sensors. Each one's got a different DEV-UEI, which is basically the serial number of each device, and last seen timestamp, the name, so 1 through 8, and then they're all basically it's using a device profile, which is basically a decoder block that ChirpStack uses. It's JavaScript pretty much, and it processes the raw payload which is a base 64 encoded block of information, into the different CO2, temperature, humidity, and barometric pressure for this particular sensor. The other really cool thing with ChirpStack is it's got all these integrations. So each application can be integrated into InfluxDB and ThingsBoard. Those are the two that we use. But it'll also do MQTT, which is just a very lightweight messaging application that dozens of other things can use to pull that data in and integrate it into other workflows that you might already have in your system. So that's really handy. You can also send it directly to AWS, to Azure, or Google Cloud. And so they all have IoT stacks. You don't have to do any work. You just enable these different integrations, and it'll forward that data simultaneously to all the integrations you want. And so we're forwarding ours to Influx and ThingsBoard. And so this is the InfluxDB, and we're just pointing it at NRP ThingsBoard InfluxDB, NRP Nautilus.io, the API, the version, and we're telling it we're writing it, the organization and the bucket, and then there's a token that's set up in the InfluxDB. And so that's how we archive the data into the InfluxDB system. And then this is the ThingsBoard integration. We just pointed at the IP address and the port number. And then each device has got this ThingsBoard access token for each device. And you just copy that out of ThingsBoard, paste it into ChirpStack, and the data shows up where it's supposed to. So this is InfluxDB. It's real-time systems. And basically, they have, there we go. The Data Explorer is one of the things I use quite a bit to figure out how to write a Jupyter notebook to parse or to grab the right data. So you can say, Iron Horse Vineyard, I want this EM500 CO2 sensor, I want the value, and I want it from these 4 payloads. And then there's a script editor. You just click that, and it gives you a piece of JavaScript you cut and paste into the Jupyter notebook, and that data just shows up. So it makes it really easy. You don't have to do this once. We publish the Jupyter notebooks with a read-only API key. This is how the National Data Platform gets it. We also have some raw Jupyter notebooks that anybody can copy and modify for their own needs. And here's the Jupyter. And all the links to this is at the bottom of these slides. So when you grab a copy of this, you'll be able to get right to it. These are all freely available. You don't need any login to the GitLab to get this stuff. But so we have these EM500 CO2 sensors, the Atmos 41 weather station, the different soil moisture probes, CO2 from SenseCap, and then the ThingsBoard. This is ThingsBoard is another open source web service we're running. I think this one is in a virtual machine. They do have a Helm chart deployed version of ThingsBoard, but they haven't been keeping it up to date, and it's kind of a pain in the butt. So it's just easier for us to deploy it in a virtual machine. But ThingsBoard is a multi-tenant, multi-user, multi-customer. This one instance could handle tens of thousands of sensors. For basically, we could have every university in California sending data to this one instance, and they could have their own logins for their admins, their own logins for their customers or their students. So it's very nicely hierarchically constructed, so you can present different things to different people. This is the map that I was talking about. This is what, right now, to create just the blocks, you have to hand code the perimeters of the block for everything. But this can pull in a GeoServer map. And so the idea is we're going to replace this base map with our own base map that's combining the Bing or Google bottom layer, adding all the layers that we want on top of it. And then each one of these dots is color-coded. They've all the sensor locations are on the map. And if you mouse over these, it'll give you the real-time statistics of the latest value coming off of that. If you click on it, it goes to the other dashboard that shows you the detailed time series from that. So like this is mousing over the weather station. And then if I clicked on that, it would take me to this weather station view. This is the EM500, my favorite CO2 sensor. And you can see the CO2 is the blue, the temperature is the green, but it looks, oh, there's something, that's got to be barometric pressure. The scale is, it's buried behind it. It scrolls a little bit apparently. And the red is the humidity. You can actually see the green is kind of nested down in the bottom of the temperatures along with the humidity. But you can see all 8 sensors in one view. This is the National Data Platform. They're pulling the same InfluxDB data with the same read-only key and pulling that into their system. And this is their metadata catalog. And so you get into here, and like we saw earlier, you can get to all this data and create your own workflows around it, publish it back into their catalog. This is an example of the EM500 CO2 sensor, again, showing the different changes. So this is the vineyard. There's LoRaWAN antennas. This is our camera tower. It's got HP-REN wildfire monitoring system. We also added a Alert California pan tilt zoom camera, but we got a little bit fancier than the ones they're deploying. Ours is 4K, and so it does extremely good to the point where we can zoom all the way across the field and watch the drone flying. And the UGCS software has an API that will tell us the geolocation of that, and then we should be able to tell that camera to track the location. Even if it's flying behind a tree, it'll always have a lock on where that drone's supposedly at. And when it comes out from behind the tree, we'll be able to see it. So that's another teleoperation plan for our future. And then the 10 gig network comes in along this wire, comes down, and this box on the wall is where it comes into the building. So it's quite nice to have. So yeah, this is just a Iron Horse vineyard. We have 4 of those Teros 22 digital routes, 4 Dragino solar-powered LSO1 sensors, 4 of the Dragino quad sensors, 2 SenseCap CO2 temperature and humidity sensors. One is inside the wine cellar, I guess they call it, where the fermentation vats are at. And we can see peaks of CO2 that we're releasing on a very regular basis. And when the time zone changed, they didn't. And so it shifted 1 hour. And so we could tell there's some automation in the building that's probably venting the tanks on a regular basis. We could also see when the forklifts drove in and out. Let's see, 8 mile site CO2 sensors. Those are my favorite CO2 sensor. 1 Atmos 41. It's a very high precision weather station. It can handle extremely high winds. It also has one of the most advanced water measuring. It's got a tipping spoon for massive flows, but it also can watch fog condensing, and it has a microliter drip counter. And so as fog condenses in the bowl, every drip is counted and falls into the tipping spoon, and then it'll empty it when it gets full. It also measures the conductivity of the liquid in the tipping spoon. So you can see if you're getting acid rain or whatever is happening in the environment there. Water pressure sensor, earthquake. Oh, and we added a UV sensor right next to the weather station. So that we have, the weather station's got a light sensor, but we also added a UV sensor because that was something that the vineyard was interested in monitoring. So this is the Mac Studio that's hooked up to 10 gig. We put in a Ubiquiti Dream Wall that gives us VPN capabilities, very secure, very high performance, 10 gig out to this Mac and 10 gig connected to that. And then all the web cameras and all the IoT sensors and everything is connected to that. And this is our Iwo Jima putting up the tower. Yeah, that was, I was able to design the camera mount using SketchUp, and then in New Mexico, I took it down the hill to a guy that had a plasma cutter, and they cut out all the parts and welded it together, and all we did was bring it home and paint it and throw it on the top. And this is the Scenic Juniper router that's in their little network closet or server room, whatever you want to call it. It's a very small space. And then to protect it, the fiber, we put it in this split loom, plastic loom to hide it from the critters in the roof. And we also use this split loom to protect all the sensor wires going down into the ground in case squirrels want to chew on something. It gives a little more time. So that's the, yep. Oh, it's done? Okay, should I continue or? It's your session. Okay, we'll roll through this. We're almost at the end. So this is the view. You can see the hills. I mean, this terrain following is very important. Otherwise you'll crash. The other nice thing is you get these mountains off in the distance, and there's hot springs all over those. And one day, a whole bunch of them went off at the same time. And so we get to see interesting things out this camera. We also saw, from the 4 cameras, we saw a aurora that came south far enough that we caught it on the time lapse. This is that enterprise gateway I was talking about, very ruggedized, very nice. A whole bunch of different things that went into and the cost of that. So it's $1,000 for all the bits and pieces to put that gateway on the pole. This is the Raspberry Pi kit for the ChirpStack OS. This is one of the Teros 22 sensors. This is one of the solar-powered SDI-12 converters. This is the quad probe, and that's these probes go on just the single temperature, moisture, and conductivity system. These are the 2 CO2 sensors that we're using. Oh, I forgot to talk about the purple air. That does particle counting so we can see if there's smoke or pollution in the area. On the local network, we can just use curl to pull the raw data off of that and push that into anything we want. And so there's another view of those sensors. This is the weather station, really small. There's the pulse counter for the water pressure, and then the earthquake sensor at the end, the CO2 sensor. There's the purple air sensor. And this is Tom and I schlepping and drilling holes, and then some of the students from Sonoma State and I and Tom out in the vineyard. And that's the CO2 sensor in the building, and there's our weather station. And I'll leave this up for a second. Anybody wants to look at the dashboards, take a picture of these QR codes. You can see the dashboards live anytime you want, and then a drone flight of something that we recently did for a presentation. And this is it. Oh, one last one. This is a brand new camera that we picked up. This is the spotted lanternfly and the European grapevine moth. If you see these, you're in trouble. They're very prevalent on the East Coast, but if these showed up at this vineyard, alarm bells would ring. The idea is this is an AI, Ubiquity AI camera that understands how to do webhooks. We're going to do basically sending anything that gets attracted by a pheromone trap for these bugs. If it comes near this little thing, a webhook will send it off to the National Research Platform for recognition, and then it'll come back to the Ubiquity hardware and send out email and text alerts to anybody we tell it to. That's it.